So we talk about I mean from last 2 weeks we start with the finite element formulations, okay, a problem especially on solid mechanics problems. We have looked into axial members, okay. Then we also look into the basic steps, okay. We have the pre-processing phase, solution phase, then post-processing. And under solution phase, under pre-processing phase, basically we are creating a global matrix. Then we solve it under solution phase. This global matrix, I mean that basically consists of a set of algebraic equations that we have to linear algebraic equation that we have to solve it simultaneously. So we have many methods. So under this matrix algebra topics, we look into different methods on how to solve, okay, that matrix, right? So we have direct and also iterative methods, right? So we also can make use of MATLAB's Excel to solve it. So this basically you have an idea of how we solve, okay, how we make use of these finite element methods, okay, from the start beginnings, okay, we formulate it, then construct the element equations, elemental equations, then assemble them into a global so-called matrix forms. Then we solve the matrix. Then yeah, we can post-process it to get other information. So these are the steps. So today we are looking into one-dimensional elements lah. I mean, what we have discussed so far, if you see that we are connecting, the problem that we have discussed previously, was an axial loading member. So we did discretize them into elements. So this element, again, when we construct that, it is more towards one-dimensional. So we look into that, I mean, a little bit on one-dimensional elements, what are they, then types of them, and also there are the what we call coordinate systems that basically can be considered later on. So different types of coordinate system that will be considered later on for our later. It will be used for our formulations on especially other types of members like trusses, frames, beams. So we should look into one-dimensional elements, types of them, then and what are the available coordinate system. So that is our focus on today. So one-dimensional elements. So if you recap back, I mean, what we have done in our previous examples, the axial loading member, axial loaded members, right? So we are assuming that that equations of the elements of one element that is linear equations F equals to K delta X, right? So one-dimensional elements, if basically when we have a one-dimensional elements, okay, we discretize, I mean, in our previous example, we discretize into elements, right? So each element we have nodes, I mean, 2 nodes. So if you want to increase, we are saying that if you want to increase the accuracies, okay, let me draw it out. So one-dimensional elements, let's say we have right. So we have these nodes, then we have these one elements, right? 2 nodes. Then we connect one elements. Maybe now we have 3 elements, 4 nodes. Okay. Here we get our so-called, we want to find our U1, U2, U3, U4. Still remember? Then we solve it. We get our U1, U2, U3, U4. Right. So in the case of if I want to increase my accuracy, meaning if I want to find, okay, what we call the displacement or deformation at, let's say, this particular point, okay, this particular point, okay, sorry, I want to find a displacement at this particular point, or probably this particular point, or yeah, probably this particular point, or here, right? So that probably not available in what we have, because what we have solved is basically we got U1, U2, U3, U4. So four nodes. Four nodes, then basically we have a deformation of exactly at here, the nodes U1, U2, and U3, U4. So in the case of I want to find the red cross positions, okay, the deformation, we cannot determine it lah. So if you want to determine all this position, then probably one of the methods, or one of the approach will be, we have to consider this particular position as a node. Okay, so we increase number of elements probably, so that elements consider so-called the nodes. Okay, so probably I can have a node at here. I can have a node at here. Okay, so I can have probably a node at here. Then we have more nodes, meaning we have more elements, right? We have more elements. Then probably we can determine that U. Solving it higher degree, or higher degree of that matrix, then we can get the deformation of that particular nodes. Okay, so if you want to increase the accuracy, or you want to determine that particular nodes, so-called deformation, or any parameters, okay, in this case, we either increase, okay, the elements, number of elements, okay, in this case it's linear elements, then, or we use a higher order interpolation function. So what we can do is, we can, okay, this is a linear elements, right? I mean, kx f equal to kwx omega delta x. So we can assume that these two nodes is basically governed by a linear functions. Okay, so we have this basically linear functions of here. So we can find, right, what is the deformations at this particular point. Okay, when we have this U1 equal to 0, U2 equals to 1, let's say, then we can find at this particular point what is this. So that we can what we call approximates, okay, making use of this linear function, even without the node itself, without the node in that particular point itself, we still can approximates that particular so-called deformation in this case, or any parameters lah. If you're using temperature, then we can approximate. So of course, if you want to go beyond, I mean, the accuracy, the higher accuracy, then probably we can increase the order of interpolation function. So from linear, can I have cubic, or can I have quadratic higher orders functions? So probably this in between this, probably we have functions, okay, of quadratics, okay, quadratics functions. Then probably we can predict a better, or a more accurate deformation in this case. So we will want to look into that. So remember, I mean, we are in approximations, again, numerical approximation, or numerical methods, or numerical approximations. Then we would want to increase accuracy, and how to increase the accuracy. The one is the what we call the size of your elements lah. So you can go smaller, then you have more nodes, right? Then you will probably have you can determine better or more accurate deformations of each nodes in this case. Or you can increase what we call the types of element. In this case, one-dimensional element, you have different orders, okay, from linear elements, you go to quadratic elements, to go higher order cubic elements. So these three types of elements, I mean, you can make use of these elements then to increase its accuracies, right? So first is the linear element, like what I mentioned to you. So if you have one element, okay, two nodes, this is your one element, okay, E, one element. So you have node I and node J with the length of L. So probably over the temperature itself, we know that at node I, the temperature is, let's say at Ti, the node J, the temperature at Tj. So any position of X, okay, X, when X or X equals to let's say L over 2, then probably we can make use of this linear function to determine the T at X equals to L over 2, right? So that is linear elements where we make use of, we know that we are assuming that the node to nodes, okay, in one element is linear functions. Okay, quadratic elements, whereas of course you have to build, you have to ensure that, or it assume that that node to nodes, okay, between one elements, it is a quadratic function. Or to build a quadratic function, you need at least 3 points, right? So in this case, you need 3 nodes, okay, within one elements, okay, from just now, okay, the same length itself, you need 3 nodes, so to basically plot the quadratic function in this case, then that assumption become valid in this case, right? So in this case, if I want to find, if it's a quadratic functions, of course we can find the node at L over, the node at L over 2, or even we can go a little bit others from this particular node, maybe the L over 3, right? Or L over 4, we can also find, and probably we can get a better predictions, okay? Because we are using the higher orders, okay, of functions, okay, compared to probably here L over 4 in this case, right? More accurate, we will say that. So, but it will need three nodes, okay, to plot that quadratic functions lah. So to make use of that quadratic elements, we need 3 nodes in one elements. So cubic elements, whereas we have let's say you have one element X with the length of L, then probably in between them, okay, we call it mid-side nodes. You need to have two nodes, additional 2 nodes in between this I and J. So that give us or allow us to plot that cubic functions. Then from there we can probably have a higher orders. Now we have higher order interpolation functions, then probably we can get a closer approximations in this particular case, right? So one dimension element, we have linear elements, quadratic elements, or cubic elements. So it's up to us which one we want to use. So what we have previously, okay, formulate, we are using these linear elements, and in the case of we want higher order, in this case we can we want higher accuracy, in this case we can use higher order elements, or we can increase our so-called number of elements, or reduce the size of our elements, right? So that is 2 ways to do that. So that is what we call type of elements. Then if we are looking into linear element itself, right? So how we come up with this so-called shape functions. So linear elements, is linear functions, right? So in that case, we are assuming that T, right? This T in one element basically is basically governed by Y equal to mx plus c. So that gives us so-called that equations, right? So if we substitute T equals to Ti, okay, then we know that is at x equal to xi. So we substitute this into these 2 points. We substitute these 2 points in this equation to find the unknown C1 and C2, right? So in this case, we have 2 equations from these 2 points itself, C1 plus C2. Then we have C1 equals to Ti equals to, this is our first equations. This is our second equation from the point of x equal to xi, that T equals Ti, x equal to xj, where T equal to Tj. So substitute into this equation, general linear equations, then we have our two equation out, rearrange it, then we have our C1 and C2 solved, right? So that gives us our C1 and C2. So rearrange the substitute our C1 and C2 into that original equations. Okay, T element equal to C1 plus C2x. Then we have this. This is our C1. This is our C2. Right. So and we want to try to rearrange again, okay, one elements, I mean in the elements, that particular element, the temperature of that particular element in terms of Ti and Tj, okay. So we have this one elements temperatures, okay, that equals to the functions, okay, Ti plus the functions Tj. So this basically we rearrange in terms of Ti and Tj. So that gives us this. Okay, that is what we call shape functions. The shape functions. Okay, so if you this thing can be simplified. It equals to this lah. This equation coming down, it will have this T element equals to Si Ti plus Sj Tj. So this Si is a shape functions at node I. Then Sj is what we call the shape function at node J. Okay. So in the matrix form, if we want to rearrange it in matrix form, then we have a T element equals to Si Ti. Okay, this is Si Ti plus Sj Tj, right? So we want to write in a matrix form, then it's a Si Sj, then multiplied with a matrix Ti Tj. Okay, 1 plus 2, sorry, 1 plus 2, then 2 plus 2, 1 times 1, 1 times 2, 2 times 1. So we get a 1 times 1 matrix. Right. So if you look into these shape functions, Si and Sj itself, then you can see that it is Xj minus X, first thing, okay? Then Xj minus Si. Sj minus Xi is actually our L, the length of L, okay? If I have my Xj minus my Xi here, then this is our so-called length. So it can be simplified to Xj minus X over L for shape function node I. Shape function node J, basically it can be represented by X minus Xi over L. All right. So that gives us representations, okay, and so-called equations that represent the what we call the elemental equations, elements, that particular one elements. So in this case, okay, it can be any unknown variables. I mean, we are using temperatures, right? So it could be deflection, velocity, anything, okay, any parameters, okay, that we want to represent. So that so-called phi itself, okay, this thing, phi elements, okay, any parameters, okay, could be represented by Si, Sj, then phi I, phi z, okay. So that is what we call elemental equations that we have for so-called unknown variable in this case, okay, for one element itself. Okay, and it is related to a shape function. So in the case of I have my nodes, okay, that is I and J. I have this node I and J uh, 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 so-called temperatures. For this case, we have the temperature node I, node J. Then with these shape functions, then we can actually find, and it is assumed that it is a linear functions, right? So if I want to find at L over 2, then probably like what I mentioned to you, then you can put L over 2 at here, your X, okay? Then we can determine our shape functions. Then eventually we can determine the temperature at L over 2 in this case. Okay, so that is in representation of our elemental matrix in under linear elements. Right. So to look into these shape functions, there are some properties or characteristics inherently. Okay, it have a value of unities. Okay, at its corresponding node, and has a value of 0 at the adjacent nodes. So what it means here, the shape function at node I, okay, equals to when you are at x equal to xi, okay, is 1, okay. Whereas shape functions at node I, when at x equal to the adjacent node is xj, is equal to 0. Okay, so that the characteristics or the properties of it, right? So same with the shape function at node j, okay, sj, when it is at the node j itself, x equal to xj itself is equals to 1. But whereas it is when it at the adjacent nodes, okay, which is at node, this shape function j at node I is have no relationship, then it is 0 in this case. Okay, so that basically give us that when you add up these two shape function si and xj itself, it will give us always give us the sum of these two shape function is equals to 1. Okay, and the derivative, the sum of the derivative of this with respect to x itself is 0 in this case. So if it is the shape function si plus sj is 1, then the the derivative of it, so okay, the derivative of these shape functions are dsi dx plus dsi this sj dx, okay, dsi, okay, dx plus dsj dx, it have to be equal to 0. So this is its characteristics. So in the case of let's say you have this point, okay, so what it means here, we have a t e equals to si t I plus sj tj, right, just now, okay, or in matrix form we have si sj ti tj tj, right? So in what it means here, if I have I want to determine my what we call the temperature as x, okay, equal to xi, right? We know that here here if x equal to xi, my xi equals to 1, xj equals to 0. So in this case, this part equal to 0, then I have xi ti, okay, which is 1 times ti. So I know that an x equal to xi, I get my temperature equals to ti. So in the case of I have my x equal to xj, right, then I know that my xi equals to 0, xj or shape function at node j equals to 1, then my t e at x equal to xj, then equivalent to tj, right? So in the other case, if I want to find my x, okay, my any x, right, x equal to any between this element itself, right, then I have my shape x at any x, the temperature T, okay, this particular element at any x itself, then we have S I, okay, multiply with Ti plus Sj multiplied with Tj. So if you have x equal to x over L, then probably you have to substitute your x equal to x over L into this shape function. So it will give us a value of a ratio or a value between these two where they add up is equals to 1. Okay, where Si plus Sj equals to 1. So probably it could be it could be 0.5, 0.5 Ti plus 0.5 Tj. Then you get the temperature of that particular element where x equal to a certain numbers. Okay, so that is where we make use of these properties of what we call the characteristics into our linear function, and we can determine from there any so-called values, okay, of the parameter that we are investigates, okay, within the nodes, okay, within the two nodes of one within one elements. Okay. Then if we are moving towards quadratic elements, right? So of course, if you have a quadratic elements, then you have this ax squared plus bx plus c, okay? So that give us a quadratic. These give us the quadratic elements there where we have three unknowns. Then three unknowns, then we need basically three equations. And here, that is the reason why we need three nodes. So in between the so-called the elements, the two nodes of the one element, then we need another node at here, right? So which is the node k, okay? Which is the node k. So we know that at x equal to xi, t equals to ti. Okay, so that is the one conditions. Then when x equal to xj, t equals to tj. Then when x equal to xk, t equals to tk, that gives us three equations lah. In this substitute into it, into this so-called equations, we have the equations, right? So again, later on, if we solve this, C1, C2, C3, right? Then we rearrange in these particular forms. Okay, then we have our 1 times 3 matrix, 3 times 1 matrix. Okay, so that gives us the elements. Okay, matrix, elemental matrix. Okay, in quadratics. If you are using quadratics elements. Okay, so here we have the three shape function now. Okay, Si, Sj, and Sk because of the three nodes. Okay, in one elements. So it could be in temperature. Of course, it could be any parameters, okay, variables. Okay, it could be in displacement, velocity, or any other parameter that we are in looking into. Right. So how to find this particular so-called shape function Si, Sj, Sk? Okay, in a more easier way, probably you can use this Lagrange interpolation functions, where it's stated that if you want to find any nodes, okay, shape functions. So what we are doing is we have this multiplication, okay, sum of these multiplications with x minus xm, okay, but we excluding x minus xk, right? Then xk minus xm, omitting or excluding xk minus xk. So what it means here is if I want to find x1, okay, we have three functions, right? We have three so-called nodes in this case, right? So we if I want to find x1, so we have the first what we call the numerators. We have this x minus x1, x minus x2, x minus x3. Okay, then we have this x1 minus x1, x1 minus x2, x1 minus x3. So what these interpolation functions, Lagrange interpolation functions, say that we have to omit this guy, right? And this guy for S1, right? So end up you have we have this x minus x2, x minus multiplied by x minus x3 divided by x1 minus x2 multiplied by x1 minus x3, right? So that gives us, if I want to find the first one, right? For node k, okay, node k or number 2 x2, okay, then we use a similar, okay, where you exclude. Okay, for node 2, we exclude x minus x2. Okay, we exclude this so-called, we have x minus x1, x minus x2, x minus x3 divided by x2 minus x2 minus x1, x2 minus x2, x2 minus x3. So this guy's gone. This guy is also gone. This is x, sorry. X minus x1, x minus x2, x minus x3. This is gone. So end up we have this. All right. So for node J also the same. Okay, when k go to 3, then we have probably x minus x1, x minus x2, x minus x3, where this is omitted. Then we have x3 minus x1, x3 minus x2, x3 minus x3. This is omitted. So that gives us the shape functions. So if you look into this itself, so we have end up we have this x minus x2 for shape function number 1. We have x minus x2 multiplied by x minus x3. Then this x1 minus x2 is L over 2. X1 minus x2 is L over 2, but it's negative, right? Then we have this so-called x1 minus x3 is also negative L in this case. So end up we have this L over 2 over L square over 2, right? So that gives us in the what we call denominator is L square over 2. So x2 minus x1 we know that is L. X2 minus x3 is L. This one is L over 2. X2 minus x3 is negative L over 2. So end up we have L square over 4. Negative L square over 4. And for this, we have L, x3 minus x1 is L, then x3 minus x2 is L over 2. Then we have, again, L square over 2 in our denominators. So end up, we have we can determine our shape functions. Okay, in this case is this 3. So again, you have the properties also. I mean, the same characteristic properties. If I having Si plus Sj plus Sk all have to be equals to 1, something like that. Okay, and if I want to find my so-called x when at x equal to xi, so my Si equal to 1. Okay, then Xj Sk equal to 0. So that characteristic still stands, right? Then cubic against the same basically everything the same, just that you have 4 unknowns, then you need 4 nodes in one element there to determine that C1, C2, C3, C4 unknowns. Okay, so if you rearrange everything, then in terms of shape function, then you have SITI plus SJTJ plus SKTK plus SMTM. In matrix form will be something similar like this, or in any general what we call parameters, then it will be like this. So this Si, Sj, Sk, Sm also can be obtained. So okay, or using that Lagrange interpolation functions, right? So probably just to so to show you, okay, a quick one. So we have Si, okay, we go to S1, right? Then we have x minus x2, x minus x3, x minus x4. Sorry. X4, where we omit the x minus x1. So x1 minus x1 also we omit, so we have x1 minus x2 onwards, x1 minus x3, x1 minus x4. So it will give us this x minus x2, x minus x3, x minus x4 divided by, here we have a negative L over 3, right? X minus x3 is negative 2L over 3, and x1 minus x4 is negative L. So it will give us negative 9 over 2L cubes, x minus x2, x minus x3, x minus x4. Right? So similar with what we are having at here. But for number 2 is node K. Okay, node K. So for number 2, Sk equals to S2, then we have our x minus x1, okay, where we omit the x minus x2, then we follow by x minus x3, x minus x4, right? So divide, the denominator will be x2 start onwards minus x1. We omit x2 minus x2, followed by x2 minus x3, x2 minus x4. So it will give us, here will be right here, x minus x1, x minus x3, x minus x4, right? Divide by x2 minus x1 is L over 3. X2 minus x3 is negative L over 3. Then x2 minus x4 is negative 2L over 3. So in this case, it will give us, here is 27 over 2L cubed. Then x minus x1, x minus x3, x minus x4. Okay, so for the other two nodes will be also SM. Here is x3, then we have also j equals to s4. Then you can find the same way, you will get what you have here. All right. So later on, we will see how we make use of this shape function in terms of different types of 1D elements. All right. So in this 1D elements, we have this coordinate system, and you see that just now we are in global coordinates. Everything, our shape functions is represented by this X capital, okay, uppercase X, XI, okay, XJ. So basically it represents usually this symbol or this capital X, or what we call global coordinate, it represents the location of each node, its orientation of each element, and when we want to apply a boundary, the loading, like what we have used to it, okay, in our first examples, okay, in axial loading, or in this so-called global coordinates, okay, in terms of their respective global components. So if your global component you have a so-called origin at here, then probably your xi, okay, will be at here, okay, and xj will be at here. So it all refer to this particular so-called origin at here. So usually it used to represent a location of each nodes, okay, orientation of each element, and also to apply boundary and loads. And we have these local coordinates. So if you have local coordinates, then probably it used to construct when we used to construct geometry, or you want it involve integrals where you have integral from where to let's say from 0 to L, then this will be involving the so-called local coordinates, right? So here, if you have a local coordinates, then probably it starts from the nodes. Starts from the node, you have this x itself, so that is represented by a lowercase or small letter s, x, okay, in this case. Then that will representing the x, okay, the position or the location of that particular so-called point or whatever particular nodes, okay, in terms of its own so-called element itself. Right. So in the case of local coordinates, in this particular case, we have learned that from the previous linear elements, right? Our shape functions for xi and xj in global coordinate is this one, right? So if we want to find everything in local coordinates, then probably my x can be represented. Okay, my x any point any point at here, x within this particular element itself, we can represent by xi plus x. Okay, from this xi itself plus x, it is equivalent to our so-called x at anywhere. Okay, any point. Okay, at any point, the capital X. So here in the globe, if you rearrange this thing, xj, it become this thing become xj minus xi plus x. Okay, divide by this is xj minus xi, which is L. So we have here become L plus x over L. So become 1, sorry, this is minus minus x. So we have here is minus, so we have 1 minus x over L in local coordinates. So similarly, if you substitute x equals to your xi from this particular point itself, this particular node itself, okay, plus another so-called x, which is our local coordinates x, then probably you will have again x over L, which is your shape function for node J. Okay. So it will be later on, you will see that when we are dealing with angles, okay, so we use uh, globals, okay, and the position of the node we use global, but when we are particularly on that particular element itself, when we have internal force, internal displacement or deformation, then we would want to use local coordinates. Then we, from the local and global, that is what we call a transformation, can be transformed easily from local to global later on. We'll see in, especially in trusses and frames later on. Okay, so natural coordinate is another coordinate system, I mean, of your elements, one-dimensional element, where it is a dimensionless forms. Okay, so it is basically what we call often usually used to when you have evaluate integral. So this dimensional form basically start from one from -1 to 1 itself, then it helps in what we call when you do integrations, right? So that involve integration of your shape functions, of your equation of formulations, then it become easier in the forms of -1 to 1s, right? So that is the mainly, okay, another forms, okay, is local coordinate, but it's a dimensionless forms, okay, with the basically it helps, okay, for an easier calculating of so-called or evaluating of your integral with the purpose of if you want to find the stiffness matrix later on, okay, elemental stiffness matrix, or if you're in temperature conductance matrix, okay, then will become easier in that case. So these natural coordinates is a local coordinate in dimensionless forms, okay, having -1 for the limit of integration. So what we have here just now, if xi is 1 minus xl, okay, we have this si equals to 1 minus x over l, sj equal to x over l, right? So in a local coordinates forms, okay. So what it does is basically it represent it with what we call xi, okay, for symbols, okay. So this xi symbol basically is equivalent to 2x over l minus 1. Then if you substitute this so-called if you rearrange this, that will become so-called here will become 2 2x minus l over l. Then you rearrange everything, then you will have this okay, xi l, okay, equals to 2x minus l. Then we have x itself, 2x itself equals to 2x itself equals to xi L plus L, then it will give us x equals to psi. Okay, we could take out the L, okay, plus 1, okay, divide by 2, okay. So in that case, if you substitute into these particular forms, then probably you will get this SI equals to this in terms of psi, okay, and SJ equal to this, and that is what we call properties. So basically, it will see that from node I itself, your shape functions now, what we call your xi itself is -1, okay. So for node J itself, your xi is 1 in this case, right? So if you substitute this -1 into here, okay, if you substitute this xi equal to 1 at Si, you substitute into here itself, then you have 1 over 2, 1 minus 1, okay, so it's equals to 2 over 2 equals to 1. So it fulfill that again that the properties of the shape functions lah. Then if you substitute this in Sj equals to psi equal to 1, then you have 1 over 2, 1 plus 1. So it's equals to 2 over 2 equals to 1, okay, for Sj itself. So that its properties are basically your psi will be basically getting from -1 to 1, then it will be useful, okay, when you are particularly you need integrations, okay, numerical integration in this particular form of your so-called shape functions when you are dealing with or with the purpose of determining or calculating the elemental stiffness, your stiffness matrix. Right? So if you have this Si and Sj in what we call a linear so-called shape functions, then the shape function equation will be Si plus Siti plus Sjdj. So substitute into it, then you will be in this particular formula. This is your Sj, this is your Si. Okay. So if you are having in these natural coordinates, one-dimensional in quadratic elements, then again you have this Si, Sj, Sk in cubic what we call elements. Then you have I, J, K, M. Okay, for nodes. Okay, for shape function in this case. Then in terms of this side. So for example, you have this just one example. If you have this Si for a cube quadratics, you have in what we call in our global coordinates that we have determined just now, we have using the Lagrange interpolation methods. You have this L 2 over L square x minus xj. Then we have x minus xk, right? So that is what we have obtained previously in global. Then if you want to convert into locals, okay, local coordinates, then we have this 2 over L square. Then we have this xi plus x, okay, small x, minus xj. Then we have this xi plus x minus xk, right? So then it gives us 2 over L square. This xi minus xj is -L plus x. Then we have xi minus xk is a -L over 2 plus x. All right. So rearrange it. Then we have this in local coordinates. We have this 2L square, 2L square, 2 over L square. Sorry, minus L over plus x, -L over 2x. Right. So that will be, sorry, that will be our local coordinates. These will be our so-called local coordinates. systems in our shape function I, okay, for quadratic elements in local coordinates. Then if I want to go into natural coordinates, then basically we have this rearrange everything in terms of our you can rearrange this, okay, equals to 2 over L square 2x minus L over 2. Then we have this x minus L, right? Then we arrange again, then we have this 2x minus L, okay, over L, x minus L over L. Okay, then we have this x over L minus 1, 2x over L minus 1. Then we substitute that what we have here is the x over L. Just now we have this xi equals to 2x over L minus 1. So if I have this in terms of x over L, x over L will be, sorry, x over L will be 1 over 2 xi plus 1. Okay, so substitute into here, then we have our, this is 1 over 2 xi plus 1 minus 1. Okay. Then we have this 2x over L is 2, basically is xi plus 1 minus 1. Right, so it will give us so-called this SI in this case at the end. Right, so that is basically how we play around with a different coordinate system. So if you look into this, basically this is just a summary, okay, for you. Okay, you can refer to it anytime. From we know that under one-dimensional elements we have linear, quadratic, and cubics. So in terms of shape functions, linear we have Si, Sj are 2. Because to note quadratic we have 3, Si, J, and K. Cubic we have 4, Si, Sj, Sk, and Sm. Right. So that in terms of global coordinates, capital X. Then in terms of local coordinates, okay, then we in terms of lowercase x. In terms of natural coordinates, we have this xi, okay, which is in this xi. If you look at this, our the length itself, I mean the one element itself, within one element itself is I and j, like in global coordinates. But then in local coordinates, this x is from 0 to L. Then if in terms of natural coordinates, our xi is in terms of -1 to 1. Right, so that gives us a summary of what's the elements, one-dimensional elements, 3 types, okay, in different coordinates.